Okay, hello everyone in a new video. So we have reached part 4 of chapter 3, which is the chapter of DC voltage in the second unit of electricity. So now in this part we are going to solve some exercises as a direct application on what we have explained previously and complete the explanation of this chapter. Then we have reached exercise number 6. We want to measure the voltage of a battery UAB using the oscilloscope. We have that UAB is positive and this is important. Now in number 1, they are telling me to draw the battery. So this is the battery. And connect to it the oscilloscope such that the phase terminal is connected to A and the mass terminal connected to B. So we know that the symbol of the oscilloscope is given by this. In which this represents the phase terminal or the channel and this represents the mass terminal, okay? So we are asked to connect the phase to the point A and the mass to the terminal B, okay? So in order to do so, first we need to identify the terminals A and B, knowing that this is the positive pole and this is the negative pole, okay? So here they are telling me that UAB is positive. So in this case we have two possibilities. So either this terminal will be the point A and this terminal will be the point B, or this terminal will be the point B and this terminal will be the point A. And this depends on the sign of the voltage UAB. So suppose if this is the point B and this is the point A, in this case we have that UBA is positive because we are measuring from the positive pole to the negative pole. Remember that in the beginning of the chapter we have said that if this is P and this is N, then UPN is positive. So here it's exactly the same. We measure from the positive pole, which is B, to the negative pole, which is A, so UBA is positive. But what we require is that UAB is positive. So for this reason, this point will represent the point A and this point will represent the point B, because in this case we have that UAB is positive, okay? Yet we didn't answer the question here. What we have done, we have identified the terminals A and B. So let me write here that this is B and this is A. Now yet we didn't answer the question because what is required from us is to show the connections of the oscilloscope to the battery. So they are telling me that the phase terminal is connected to A, so this is the phase terminal, and the mass terminal is connected to B. So this is it. Okay? So we could have done, for example, this is the phase terminal and this is the mass terminal. It's not important whether they are up or down, or one of them is up and the other is down. This is not important. But here let me say the following. They didn't mention anything about an electric circuit. So if someone connects the terminals A and B like this is considered to be wrong, because here we don't have an electric circuit. We are only mentioning the battery and the oscilloscope. So this is it for part 1. Now in number 2, they are telling me what does the oscilloscope measure, UAB or UBA justify, and this can be determined by referring to the connections of the oscilloscope. So notice that since the phase terminal is connected to A and the mass terminal is connected to B, then the oscilloscope in this case measures UAB from the phase terminal to the mass terminal. Okay, so since the phase terminal is connected to A and the mass terminal we know that always the oscilloscope measures from the phase to the mass. Then let's say the oscilloscope measures UAB. Notice that the oscilloscope can measure UAB or UBA, and this depends on the connection of the oscilloscope. Now in number 3 they are telling me now the luminous line is displaced downward. Okay, so displaced downward means that it's measuring a negative voltage. What does the oscilloscope measure, UAB or UBA? Justify. So first, let's give the explanation of the downward displacement due to the oscilloscope. So let's say, since the luminous line is displaced downward, then the oscilloscope measures negative value or negative voltage. It's the same. So let me write value. In this case, if UAB is positive, then we know that whenever we flip a sign, we flip these two letters, we gain a minus sign. Then in this case, UBA is negative. Then between the brackets, let's mention that UBA is negative, knowing that UBA is negative. So if the oscilloscope is measuring a negative value, and we know that UBA is negative, for this reason the oscilloscope is measuring UBA. Then the oscilloscope measures UBA. So in this case, for example, okay, so we have finished for this exercise. In this case, the connection of the oscilloscope will be like this. So the phase turn will be at the point B and the mass turn will be at the point A. But this is not required from us, okay? Then this is it for exercise number 6. Now in exercise number 7, they are telling me in each of the following cases, calculate the voltage measured by the oscilloscope. So this is the screen of the oscilloscope and this is the luminous line. Then referring to the vertical sensitivity indicated on the screen of the oscilloscope and the number of divisions displaced by the luminous line, we can determine the voltage measured by the oscilloscope using the formula U is equal to SV multiplied by Y. Okay, notice that here the voltage U doesn't carry any labels because the purpose of this exercise is only to calculate the voltage U. So let's start by number 1. Always in physics, whenever we need to calculate a quantity, we always start by writing the formula, which is given by U is equal to SV multiplied by Y. In this case, no need to construct a triangle because this is the quantity that we are interested in calculating. Now the value of SV is indicated here in the SI. As for the luminous line, this is the luminous line. Notice that the luminous line is displaced upward. So first of all, it's positive. Now we need to indicate the number of divisions. So notice that each division represents 1. So this is 1, 2, 3. This is minus 1, minus 2, minus 3. So in this case, the value of Y is 3. Now plugging this on the calculator, then the value of U is given by 6. Since SV and Y are given in the SI, so the value of U will be in the SI, which is volts. So in this case, the voltage measured by the oscilloscope is given by U is equal to 6 volts. Now in number 2 also we need to determine the voltage U measured by the oscilloscope. So U is given by SV times Y. We always start by writing the formula. So usually this we give it half a mark. Now the value of SV is given by 1.5 in the SI. Now notice that the luminous line Y is displaced upward, so it's given by plus. Now we need to determine the number of divisions. So each division corresponds to 1, 2, 3. Now what about the subdivision? Each subdivision corresponds to 0.2. So we add here 0.2, then it will be given by 0.4. This is 0.6. This is 0.8. So this is 1, and this is given by 1.2. Now plugging this value on the calculator, then the value of U is given by 1.8. Since everything is expressed in the SI, so the value of U will be in the SI, which is volts. Then the voltage U measured by the oscilloscope is given by 1.8 volts. Now as for number 3, the voltage U is given by SV times Y. The value of SV in the SI is given by 4. Now notice that the luminous line is neither displaced upward or downward, so the value of Y in this case is 0, because it is at the center of the screen. So the voltage U measured by the oscilloscope is 0. Eventually here, no need to write a unit because anything multiplied by 0 is 0. Then the value of U is given by 0. Now as for number 4, the voltage U is given by SV multiplied by Y. The value of SV is given by 3. Always in physics we need to write the formula, and here no need to construct a triangle because this is the quantity that we are interested in calculating. Now notice that in this case the luminous line is displaced downward, so we have a minus sign. Now let's count the number of divisions. Here we have 1 and this is 2, so this is given by minus 2. Plugging this on the calculator is given by minus 6. Since SV and Y are expressed in the SI, so the value of U will be expressed in the SI, which is volts. So U is equal to minus 6 volts. Now as for number 5, U is equal to SV multiplied by Y. The value of SV is given by 1. And the luminous line is displaced upward, so it's positive. Now what about the number of divisions? If this is 1, this is 2, then this subdivision is given by 1 at 2.2, and this one is given by 2.4. So it's given by 2.4. Plugging this on the calculator, then the value of U is given by 2.4 volts. So U is equal to 2.4 volts. And here notice the following. So here the unit of the vertical sensitivity is given by 1 volts per centimeter, whereas here the unit of SV is given by volts per division. And what's the difference between them? So let me say here that, okay, we can also have that SV is equal to 3 volts per centimeter, okay? So when SV is expressed in volts per division, then the unit of Y, so in this case Y is equal to minus 2 divisions. Then Y will be expressed in divisions. Now in this case Y will be expressed in centimeters, okay? So what does this represent? For each division, so this is labeled by divisions. So it is 1 division, 2 divisions, etc. Okay? But if the vertical sensitivity is given by volts per centimeter, then each division will represent 1 centimeter, 2 centimeters, okay? Now in number 6, then U is equal to SV multiplied by Y. The value of SV is given by 2.5. Now the luminous line is displaced upward, so Y is positive. Now what about the number of divisions? This is 1, 2, and this is 3. In this case, because the unit of SV is given by volts per centimeter, then Y is given by 3 centimeters. Now plugging this on the calculator, then the value of U is given by 7.5. Since everything is expressed in the SI, so the value of U will be in the SI, which is volts. Then U is equal to 7.5 volts. Now part 7, U is equal to SV multiplied by Y. So notice that here SV is given by 2.5 millivolts per division. Notice that previously the unit of SV is given by volts and not millivolts. Later on I will discuss the conversion of unit, I think, in part 5. But now let's take it for granted from millivolts per division into volts per division. We simply divide by 1000. Okay, so 2.5 divided by 1000. So the value of SV in the SI is given by 0.0025 volts per division. Okay. So always we need to convert the quantities to the SI. Now what about the value of Y? The luminous line is displaced upward, so it's positive. And as for the number of divisions, this is 1, 2. Now plugging this on the calculator, then the value of U is given by 0.005 volts, because everything is expressed in the SI. Now U is equal to 0.005 volts. And finally, as for number 8, U is given by SV multiplied by Y. Now notice that here SV is given by 8 kilovolts per division. Then in order to convert from kilovolts per division into volts per division, we simply multiply by 1000. Then A multiplied by 1000, then this is given by 8000 volts per division. Now as for the value of Y, notice that Y is displaced downward, so it's given by a minus sign, and the number of divisions is given by 1. So this is given by minus 8000 volts. Then U is equal to minus 8000 volts. And now let's move to the next section, which is section number 15, and it's given by indications on electric components. Then let me write down here section number 15, indications. On electric components. Then let me say sometimes electric components So what do I mean by electric components? For example, say a lamp, heater, washing machine, dryer, etc. Comes with indications. Or inscriptions. Now, let me give the following example. Given a lamp L, with the following indications. So suppose we have a lamp L that carries the following indication. On the lamp L, we can read the following indications: 12 volts and 0.5 amperes. Then we are interested in answering the following question: what does these indications means? Now, usually physical quantities are referred to their units. Now notice that this number carry the unit volts, so this quantity represents the voltage. So what do we mean by 12 volts? 12 volts is the rated voltage of the lamp L, under which it functions normally. Then whenever we have a lamp L that carries the following indication, which is 12 volt, this means that in order for the lamp L to shine or functions normally, it must be fed by an applied voltage given by 12 volts, okay? So usually these numbers are referred to as the indications or the rated voltage or the rated current. Now as for 0.5 amperes, then amperes refers to the unit of the current, so this quantity represents an electric current. Then it's given by the rated. Why we call it rated? Because it's simply being labeled on the lamp L, so it's the rated current under which it functions normally. And these indications or inscriptions are essential in order to describe the functioning of the lamp. For example, the first case that we consider, if you connect this lamp to a voltage source delivering a voltage which is less than 12 volts. So here I repeat, by 12 volts, it means that in order for the lamp L to function normally, we need to give it an applied voltage which is given by 12 volts. Now what happens, for example, if you connect this lamp to a battery delivering, for example, 6 volts? So 6 volts is less than 12 volts. What will happen in this case? So then in this case, let me say that the title of idea number 1 is less than the rated inscription. So let me say if the applied voltage is less than the rated voltage, so in this case we are connecting the lamp to a voltage source which has an applied voltage which is less than the rated voltage. For example, it could be 6 or 4 volts. Then in this case, then the lamp will not function. So let me say may not function. Or it may not function, or we can say it can function weakly, or function weakly. So if it functions, then it will function weakly. Now similarly for the current, if we know that if the traverse current, so here let me stress on the following: we call the voltage that we are applying to be the applied voltage. As for the current, we call it to be the traverse current. If the traverse current is less than the rated current, so in this case the rated current is given by 0.5 amperes. If the traverse current from the battery is given by, for example, 0.2 amperes, which is less than 0.5 amperes, then the lamp may not function or function weakly. Then this is one of the cases that we may consider. Another case that we may also consider, which is important, if the rated inscription is equal to the applied and the traverse current. So let me say equal to the rated inscription. Then let me say in idea 2a, if the applied voltage is equal to the rated voltage, then in this case, then the lamp will function normally. And similarly, if the traverse current is equal to the rated current, then the lamp will function normally. Finally, another important case, which is the final case that we can consider, in the case where the applied and the traversed current, applied voltage and traverse current is greater than those of the inscription. So let me say greater than the rated inscription. Now here, suppose that this lamp, which has a rated voltage to be 12 volt, we connect it to a battery having, for example, 20 volts. So 20 volts is greater than 12 volts. Then here we have a possibility that the lamp may burn out or function strongly. So let me say if the applied voltage is greater than the rated voltage, then the lamp may function strongly or burns out. Now similarly as for the current, if we now are comparing the traverse current with the rated, so let me say idea part B, if the traverse current is greater than the rated current, then the lamp may function strongly or burns out. So as a direct application on this explanation, let's solve the following exercise, which is exercise number 8. So they are telling me consider a lamp L bearing the following inscription. So we have a lamp L carrying the following inscription. So for example, one of the questions that we may encounter in solving such type of exercises is what is meant by the following indication. By referring to the previous explanation, we can see that the meaning of this indication 6 volt is the rated voltage of the lamp under which it functions normally. But this question doesn't exist in this exercise. Okay, so now let's continue. So this lamp bearing the indication 6 volt is connected directly across the terminals of a generator G, delivering a DC voltage UG of adjustable value. So here we have a battery, say for example, of voltage UG, and this we can adjust it as we wish. For example, UG may be 1, 2, 3, up to 20, say for example, volts. Okay. So now according to the values, to the value of G, we will describe the functioning of the lamp. Now they are telling me what happens to the lamp if we adjust UG to 4 volts. So notice that now the voltage of the battery, which is given by UG, is equal to 4 volts. and we always compare. So this is set to be the applied voltage. Why this is the applied voltage? Because this is the one that we are applying for the lamp, and this is the rated voltage. Now notice that in this case the applied voltage is less than the rated voltage. So let's say, since the applied voltage is less than the rated voltage, of the lamp L, and between brackets let me say 4 volts is less than 6 volt. And now here the students may face the following, may be confused with the following, is to say that 6 volts is greater than 4 volts, so the lamp may function strongly or burn out. Notice that we always must compare the applied voltage to the rated voltage. So we always start by the applied voltage and we compare it with the rated voltage. So 4 volts is less than 6 volt, and we never start with the rated voltage to compare it with the applied voltage. Okay, so in this case, since the applied voltage is less than the rated voltage of the lamp L, then we can say then the lamp L may not function or function weakly. So we don't know whether it will not function or function weakly. For this reason, we need to mention both. Now in number 2, they are telling me if UG is equal to 6 volt. So now the voltage of the battery or the DC source is set to be 6 volt. Now they are telling me then the lamp functions normally, justify. So we always compare the applied voltage to the rated voltage. Notice that in this case they are equal. So we say since the applied voltage is equal to the rated voltage, of the lamp L, and between brackets let me write 6 volt is equal to 6 volts, then the lamp L will function normally. Now as for part 3, they are telling me describe the functioning of the lamp if UG is equal to 10 volts. So notice that in this case this is the applied voltage, 10 volts, which is greater than the rated voltage 6 volt, and we are in the third case. So the applied voltage is greater than the rated voltage, then the lamp may function strongly or burn out. So let's say since the applied voltage is greater than the rated voltage of the lamp L. So here we have the lamp L. So between the brackets, let me say that 10 volt, which represents the applied voltage, is greater than the rated voltage, which is 6 volt. Then in this case, then the lamp L may function strongly or burns out. Then this is it for exercise number 8. Now let's move to the next section, which is identical lamps in series. So let's consider the following electric circuit. We have a DC generator UG connected to two lamps L1 and L2 that are in series. Now consider the following question. Consider the above electric circuit consisting of a battery of 12 volts. So let me label this voltage here, 12 volts, and two identical lamps L1 and L2. So by two identical lamps means that they are exactly the same. Okay, so number one, let's answer the following questions. Number one, so they are telling me what is the voltage across each lamp. Now here in this case, because these two lamps are in series, we can apply the law of addition of voltages, and we say that UG is equal to UL1 plus UL2. Okay, so the sum of the voltages of these two lamps must be equal to that of the battery. But moreover, the two lamps are identical, which means that they are exactly the same. Then let me write down, since the two lamps are identical, so how do we translate this statement mathematically or physically? Because they are identical, then each one will have the same voltage. So this voltage will be exactly equal to this voltage. So suppose that this voltage is U and this is U, and the sum of these two is equal to 12. So what's the number that we added it twice and give us 12? Is simply 12 divided by 2. So each of these lamp will consume a voltage which is given by 6 volts. Then in this case, because the two lamps are identical, then they have the same voltage. In this case, we say that the voltage of the lamp L1 is equal to the voltage of the lamp L2 is equal to the voltage of the generator divided by the number of lamps we have. Here we have 2 lamps divided by 2. So this is 12 divided by 2, which give us 6. Since 12 is expressed in SI, so the voltage of the lamps is expressed in the SI. Then the voltage UL1 of the first lamp is given by 6 volts. And the voltage of the second lamp is given by 6 volts as well. So let me answer number 2 here. Now they are telling me if we added a third identical lamp in series, what would be the voltage across each? So let me add here another lamp in series. So suppose that this is the lamp L3. And now they are asking me about the voltage across each lamp. So this is UL1, this is UL2, and this is UL3. So what is the voltage across each? We know that according to the law of addition of voltages, the sum of these voltages must be equal to 12. And because they are identical, then each one will have the same voltage. So let me say, since the 3 lamps are identical, then they have the same voltage. Then simply in order to share this applied voltage to the 3 lamps, we divided 12 volts by 3. Then we can say that UL1 is equal to UL2 is equal to UL3 is equal to the voltage of the generator, which is the applied voltage, divided by 3. Why 3? Because here we have 3 lamps, which is equal to 12 divided by 3, which is equal to 4. Since 12 is expressed in volts, then all of these voltages will be expressed in volts. Then we have that UL1 is equal to 4 volts. UL2 is equal to 4 volts. And eventually UL3 is equal to 4 volts. Okay, so this is it for section number 17. Now let me consider the following application. And now let me label some points. So suppose that this is the point P, this is the point A, and this is the point B, C, and N. And suppose that UG is given by 12 volts. Then let's suppose that, okay, let me label everything here in black to clarify that this is the given. So this is P, A, B, C, and N. And let me say the following question. Calculate, so UG is equal to 12 volts. This is given. And let's say calculate UAC. And number 2, let's say deduce the voltages UAB and UAC across the lamps L1 and L2 knowing that they are identical. And here on the right, let me answer the following questions, okay? So number 1, they are telling me to calculate the voltage across the points A and C, and this can be done using the law of addition of voltages. Then let me write apply law of addition of voltages. Then how do I apply this law? Always on the left to right, the voltage of the battery, which is given by UPN. And on the right hand side of this equation, we'll go from the point P to the point N across different electric components, keeping in mind that we require that UAC must appear in the equation because we are interested in determining or calculating UAC. Then from P we will go directly to the point A. Now here notice the following. From A we can go to the point B or directly from A to the point C. So we have two choices. Either we go from A to B, then B back to C, or from A to C directly. But since we require that UAC must appear in the equation, then we will go directly from A to C and from C back to N. So here I didn't break the rule because on both sides we have started with P, on both sides we have started with N, and each letter we have inserted it twice, okay? Knowing that we are interested in determining the value of UAC. Now the value of UPN is equal to 12, this is given. UPA across the terminals of P and A we have a connecting wire. We didn't justify this previously, so let me write here between the brackets that UPA is equal to 0, and the reason is given by a connecting wire. As the voltage UAC, we will keep it as an unknown because we are interested in determining UAC. Plus UCN, which is given by 0 because across the terminal C, and then we have a connecting wire. Then UCN also 0, and the reason is given by connecting wire. Then in this case, simply UAC is equal to 12 volts. What's the type of this equation? This is a linear equation and one unknown. The unknown is UAC. Okay, so here before I proceed to number 2, let me correct the following. So this is not UAC, it's given by UBC. So the voltage across the lamp L2 is given by UBC. Okay. So now in number 2, they are telling me deduce the voltages UAB and UBC across the lamps L1 and L2, knowing that they are identical. And by deduce, it means we need to use the previous part. First, let's start with the following statement that they are identical, and this can be translated by they have the same voltage. So what does it mean then they have the same voltage? Let's translate this statement into a mathematical equation. The voltage of the first lamp is given by UAB. So we have that UAB, which represents the voltage of the first lamp, is equal to the voltage of the second lamp, which is UBC. And now how do we proceed? Recall that they are telling me deduce, and by deduce it means that we need to use the previous part. In the previous part you have determined the voltage UAC. What does UAC represent? It is the applied voltage across both lamps L1 and L2. Since they are identical and according to law of addition of voltages, the sum of these voltages must be equal to the voltage UAC. Then simply here we place UAC divided by 2. Why 2? Because 2 represent the number of voltages we have across the lamps, or the number of lamps. Notice that in this case UAC is equal to the voltage of the battery simply because they are connected in parallel, okay, or according to this law. Now the value of UAC, so notice that how do we read this equation? We have started with A, we have ended with C, and B will cancel up, okay? So the value of UAC that we have determined is given by 12. And I repeat, why UAC? Because the voltage UAC represent the voltage across the two lamps, and we divide them by 2 corresponding, or 2 because we have 2 lamps, okay? So it's 12 divided by 2, which give us 6. Now because 12 is expressed in the SI, which is volts, then 6 will be expressed in the SI, which is volts. Then in this case, UAB is equal to 6 volts, and UBC is equal to 6 volts. So notice that in this case, in both cases, in this example, in this application and in this application, in both we have determined the applied voltage across each lamp when we have two identical lamps connected to a 12 volts DC source. But in this case, we use the names of the lamps. In this case, we have used the methods of the points, okay? So both of them are important, okay? Now what about identical lamps in parallel? So let's consider the following question. Consider the previous electric circuit. So this is the previous electric circuit consisting of a battery delivering a constant current I is equal to 1.5 amperes. So let's label this a traverse current on the electric circuit itself. So what's the current traversing each lamp, knowing that they are two identical lamps? So how does identical lamps is formulated mathematically or physically? It means that they have the same current. So we know that according to law of addition of currents, I must be equal to I1 plus I2, because the current I at this point splits into two currents. Knowing that I1 must be equal to I2, then in this case each current will carry 0.75 amperes, because the sum of this current must add up to 1.5 and they must be equal, okay? So let's say, because they are telling me they are identical lamps, then let's say since the two lamps are identical, then they have the same current. So the current traversing the lamp L1 is denoted by I1. This is equal to the current traversing the lamp 2, which is denoted by I2, must be equal to the main current divided by the number of lamps, which is given by 2. So it's equal to 1.5 divided by 2. Since this is expressed in the SI, which is amperes, then this will be expressed in the SI, which is amperes, okay? So I1 is equal to 0.75 amperes, and I2 is equal to 0.75 amperes. Now as for the second question, they are telling me if we added third identical lamp in parallel. So let me add another lamp L3 in parallel to L2, and let's denote its traverse current by I3. So what would be the current traversing each? Knowing that the three lamps are identical, then let me say, since the three lamps are identical, then they have the same current. So in this case, the current traversing the lamp L1 is given by I1. It's equal to the current traversing the lamp 2, which is I2, which is equal to the current traversing the lamp L3, which is I3, which is equal to the main current, which is given by I. So notice that here, divided by 3. I will refer back to this. Notice that here the drawing is not accurate in a sense that we should have connected this wire like this, okay? So notice that I in this case splits into 3 currents at this point. Say for example, if it's like this and given by I1, I2 and I3. So for this reason we have divided I into 3, because we know that according to the law of addition of currents we have that I is equal to I1 plus I2 plus I3. So the sum of these 3 currents must be equal to I. Moreover, they are equal. Then 1.5 divided by 3, this is equal to 0.5. Since I is expressed in amperes, then the values of I1, I2 and I3 are expressed in amperes. Then we have that I1 is equal to 0.5 amperes, I2 is equal to 0.5 amperes, and eventually I3 is equal to 0.5 amperes. And now finally, for the final section of this chapter, which is given by converting units. Then let me write section number 19, converting units. So let's recall the SI unit of the 2 physical quantities that we have introduced in this chapter, and they are given by the current and the voltage. Let me start by the voltage and say the SI unit of the voltage is volts, and its symbol is V. So we say V, which is given by volts. Now as for the current, the SI unit of the electric current, or let me say of the current, is amperes, and its symbol is A. Then A stands for amperes. And we should have the ability to convert from a certain unit to the SI. Then let's say the conversion of the units to the SI is done using the following table. So what does the following table represent? Okay, if we are moving from left to right in the direction of this arrow, we multiply. If we are moving from right to left in the direction of this arrow, we divide. So as we move, we multiply by these numbers according to these subscripts. Now, what does these subscripts stands for? Capital M for mega, capital K for kilo, small h for hecto, dA for deca, D for deci, C for centi, M for milli, mu for micro. So this is a Greek letter. It is given by mu. Okay. Now, suppose that we need to use this table in order to convert between voltages itself. So we label all of these empty spaces by voltages. So the first thing that you are interested in converting from kilovolts into volts. Now in order to convert from kilovolts into volts, we move from left to right and we multiply by 3 tens, which is 1000, okay? So then in order to convert from kilovolts into volts, we multiply by how many tens? 3 tens, corresponding to 1000. So this is the first formula that we can extract from the table. So in order to convert from kilovolts to volts, we multiply by 1000. And this K is similar to the one of the social media. If we have 1.1K views, which means that 1100. So K, we are simply multiplying by 1000. And in order to convert from volts to kilovolts, we divide by 1000. Okay, so this is the first conversion that we are interested in. So we must not forget this. Okay, I don't expect that all of you will memorize this table, but at least this we must memorize. Okay, now another one that you are interested in is converting from millivolts into volts. So from millivolts into volts, we are moving from right to left. So we should divide by how many tens? By 3 tens, which means that we need to divide by 1000. So in order to convert from millivolts to volts, we divide by 1000. And in order to convert from volts to millivolts, we multiply by 1000. So for example, if given 2.5 kilovolts required to be converted to the SI, so 2.5 multiplied by 1000, then this is given by 250 volts. Okay, so now we have extracted these two conversions by labeling this table in terms of V. Now what about A? So we can use this table for any physical quantity. Now here in this case we are using it for volts and amperes. So let's label the empty spaces by amperes. And we are interested in converting from milliamps into amps. So in order to convert from milliamps into amps, we move from right to left by how many tens? By 3 tens, which means that we are dividing by 1000. So, and from amps to milliamps, we multiply by 1000. So this is the third important rule that we are interested in. Okay, so for example, if the current I is equal to 200 milliamps, so in order to convert from milliamps to amps, we divide by 1000, then 200 divided by 1000, this is given by 0.2 amperes. Okay, so that's it for me in this video, guys. In the next part, we will solve some exercises as a direct application on what we have explained in parts 1, 2, 3, and 4.